After looking at different existing models which will help us get better results, let's now understand transfer learning and fine-tuning. In order for us to better understand the notion of transfer learning, it's important that we understand or visualize the different features which the conv layers generate, or which different layers in our models generate. Now suppose we have this conv layers stacked, so we're just considering just some plain conv layers with some max pool layers, and then obviously we end up with fully connected layers such that we can do some classification at the end. Now if we plot out the different feature maps after the different convolutional layers, we should get maps like this. So we're supposing we're starting from the inputs or around the input, then as we move deeper on the model right up to this layer which is coming just before the fully connected layers, there is a great difference in the kind of feature maps which are being generated. As we can see here, for the very first layers, the feature maps actually look like the original image or some of the feature maps. Note that this 4 images represents 4 different channels. Although in this conv model there are many more channels, we just selected these 4 different channels for illustrative purposes. Now we have this input which kind of looks like, or where some of the channels look like the original image, and then in the input 2 some of the channel actually don't look again the same like the original image. There's been some conversions, and as we go further we notice that the model is now paying more attention to some low-level features. By low-level features we mean the model is paying more attention to some low-level details or some pixel level details. Now if you look at, for example, this channel, this one we have pinpointed, you'll notice that this is some sort of edge detector. As based on something like this looks like the original image, the edges are being selected, or we could say some of the edges are being selected and the others aren't. That's why you have this purple color on the background, and then you have this yellowish, different yellowish patches. You could also see here that you have some sort of detector too, and basically we could see this as different edge detectors. So for this we have edge detectors even right here in some of these channels, even in on the very first layers or very first feature maps, we already have detectors or edge detectors or different kinds of detectors which detect some details which at first sight we humans don't necessarily take great notice of. That's to say that when you look at a dog, you don't necessarily check to see whether there is some edges around the portion of the ear. You don't necessarily check to see all these horizontal edges which this particular feature map is trying to portray right here. We don't necessarily check to see all this kind of information which is embedded in this image or on the doc input image, which the ConvNet actually emphasizes on the early stages of the conv layer or the conv model. Now as we go further, we notice that the conv model isn't much interested in this low level pixel level features or this low level details. It's more interested in seeing whether an image which has been given to it is a dog or is a cat or is a house or is a car or it's a bottle or something like that. So as we go further, the model is now interested in more high level features. So it's less interested in all this pixel level, low level details. As we could see, now it's interested in just classifying. So it's more interested in the domain or the problem it's trying to solve. And with this kind of knowledge, we see clearly that if we've pre-trained a model, or if we've trained a model and that once we pass an image, is able to filter out all these low level features, then it's needless for us to always have to pre-train or train our models whenever we're working with images, since with one model which was trained on a certain set of input data, we can use that same model on some new data, such that when that new data is passed into the model, it basically extracts all these low level features for us. And then once we are getting towards the end of the model, or as we go deeper into the model, we can now cut off some portions of the initial model. So what we're saying is we have an initial model like this one, and then we cut off some portions and replace it maybe with just these two layers after, since maybe if we have this model which has an output of 1,000 neurons, and that we want now to classify whether an image belongs to 200 classes instead of 1,000 classes, we can now cut off this last part and then replace it with just these two fully connected layers, such that our output can classify, or our output can be used to classify 200 different categories instead of 1,000 categories as before. But what's important to note here is the ability for the same model to be used in another task, since one model has been used already to extract, or has been trained already to be able to extract these very important low-level features which are found in images. And so since these low-level features are in all sorts of images, or these low-level features are common to all images, we can use the same model in another problem while just modifying the sections which have to do with the high-level features, which are more specific to the task. Now let's take a simple example. Suppose we have trained a model. Suppose we have trained a VGG16 model, or a ResNet model, or an InceptionNet model, or an EfficientNet model on the ImageNet. The ImageNet is about 14 million images. And after training this model, let's say it's a VGG16 model on the 14 million images, we've given that model the ability to extract as many low-level features as possible. Now, our task is on the tiny ImageNet and not the ImageNet. The ImageNet is 1,000 classes. The tiny ImageNet is on 200 classes. Now we're having to classify an image and say whether it belongs to one of the 200 categories or not. But given that we've already trained an initial model on the ImageNet, which is on the 1,000 classes, what we'll do simply is that if we have this model which has been trained, we are gonna cut off the model from at a certain point, or cut off the model once we start working with the fully connected layers. That's towards the top, that's in fact at the top, and then replace that top with a top which is more adapted to the kind of problem we're trying to solve. And in this case, we are going to replace it with a top which will take into consideration the fact that at the very end we need to have 200 different neurons and not 1,000 neurons. Another advantage is that we don't always have to come and retrain this model every time we have a problem. We can just use a pre-trained model and then change the top such that it could suit the needs of a particular problem we are trying to solve. This technique is greatly used in practice, and TensorFlow helps us in doing this very easily. Another technique is that of fine-tuning. When doing transfer learning, we didn't only modify the top of an initially pre-trained model, but we also froze the conv base, that is these conv layers, such that the weights aren't trainable. In that light, when training the model, these weights are left off and they are actually used as feature extractors. So basically we use the pre-trained weights as feature extractors to extract the low level features, while these layers at the top have weights which can be trainable. And so when training a model using transfer learning, it's only those layers at the top which are trainable and which have weights which are actually modified during the training process. Now with fine-tuning, we actually modify some of these layers such that some of this conveyor base or some of these layers of the conveyor base towards the top can be trainable, or even in some cases of fine-tuning, all the model is retrainable. So we've pre-trained the model and then we are retraining all the whole model again. We shall see that doing fine-tuning is very dangerous if we don't take certain considerations. For now, what we have to notice, to do transfer learning, we'll take off the top, we'll replace it with a kind of top we want to work with, we render all these other layers non-trainable, and then with fine-tuning, some of the layers like these 3 layers at the top are actually trainable. Let's see how transfer learning is done practically. Now we have this base model which is built from the TF.Carousel applications model, and where we extract this VGG16 model. We'll specify the input shape, we'll say whether we're going to include the top or not, and then we have the weight which is gotten from training this VGG16 on the ImageNet dataset. Now this is some good news for us because we don't always have to rewrite the code for the VGG16 or some other model which is already found in this TF.Carousel applications module. So let's run this, and then we have the summary. Considering that we have this input, we have the summary, and then we go right up to this max pooling layer. Now let's include this. So we have true, so let's include the top so that we have the full model. Like this, we have true. Run it again. We have this error because we have to take this to be 224. 224. Now everything's okay. We see that after this max pool, we have the flatten layer which flattens out this. We have the fully connected, and then this 1000 neuron output. And as we have seen, what interests us here is actually this section going upwards, as it's here that we have the feature extraction, where we extract the low level features of the image, whereas from this we actually say whether a particular image belongs to a particular category or not. And this is highly dependent on the problem we're trying to solve. Now we are working with tiny ImageNet which needs an output of 200, so it's logical that we shouldn't include the top right here, so we could say false. Then we'll run it again. We have this. Now before going ahead to train this model we've just gotten, auto apply transfer learning, let's see how to generate the kind of visualizations we saw on the slides. Also, we could see the list of the different models which are made readily available for us by TensorFlow. We have the DenseNet. We haven't treated this particularly, but the efficient nets, we've seen them with the different variants. Inception ResNet, which we didn't see, Inception version 2, MobileNet, MobileNet version 2, MobileNet version 3 large, MobileNet version 3 small, NASNet, ResNet, and then VGG with finally this exception model. So these are models which you could easily get, or we could get readily, which are made available for us by TensorFlow, and also with the weights. So since we always have these models and then we have the trained weights, the TensorFlow team has already trained these models on ImageNet. So what you will just be doing many times is you will be using these models and the weights which have been trained by the TensorFlow team on the ImageNet already. In order for us to visualize the different feature maps which are generated after this different conv and max pool layers, we're going to create a new model. Now this new model, we take this as input, so it's going to have the same input as the input of this model, but it's going to have different outputs, or it's going to have many outputs. Now the many outputs of this new model we're going to create are going to be made of the intermediate outputs of this other model. So this is going to be an output, this output, this output, and right up to the end. And we can obviously select the layers which, or the feature maps which we want to take as outputs. So the output of passing an input into this will give us obviously an intermediary output. So that output will be one of the outputs of our new model. Let's see how we could go about this. So we have this layer in the model because we've defined this as model, as we had right here, model, which was the base model, and the model.layers. So we're going through all the layers. So for layer in model.layers, we have layer.output. Now we stack all these different outputs or feature maps in a list, which is the layer outputs list. So we could say it's feature maps. So here are our feature maps, and then we define this new model called activation model, and then it has input, this model's input, and then outputs the feature maps. So its output is the feature maps. So there we go. With this we could print out, or we have activation model.summary. Run this. It's going to be similar to what we had right here. And now if we want to modify this, so we could say, for example, we want to get just the first 5 layers. So we select the first 5 layers, run this again, you see it just gets the first 5 layers. Now let's suppose we have this test image from the dogs versus cats dataset. This dog 1929.jpg is a dog, and then we pre-process this dog image. So we load the image. Here we have test image, which is basically this. We have the color mode, we have the target size. Now these images have higher resolutions compared to that of the tiny image net. So after converting to tensor, we now apply the predict function, since this activation model is a model we had defined previously. And note that this model has several outputs, where the outputs are the intermediate feature maps which are generated by the model. So if we have this, we've decided to collect the first 5, so that's why we have this. And then these are the outputs, like the outputs or the intermediate feature maps gotten after passing inputs via this layers are the outputs of this activation model. So that said, we have this the predict of tf.expand dims. Now here is for us to leave from dimension 2 to 4, 2 to 4, 3, 2, 2 to 4, 2 to 4, 3, but by expanding the dimension. So we have here 1, and this is the kind of shape our predict needs, or the model needs to predict. So that said, we have that, we run this, and then we have our activations. Now we could print out activations 0.shape, and then for I in range say 5, print this out, we'll print out the different shapes. Now let's convert this, we have I. So that's it. Now we have those different shapes, and we could see clearly that they coincide with what we had previously. That's the shapes of the intermediate feature maps. So we have this 2 to 4, 3, 2 to 4, 64, and so on and so forth, right up to 2 to 4, 128. So that's exactly what we expect. And these form the output of our activation model. Then the next step is to visualize these feature maps or to visualize the output of this activation model. Now we'll define the image size. It should be noted here we're using matplotlib, which permits us set the figure height and figure width. So we just consider this to be the image size. We've defined it to be 4. Number of channels, which we are going to print out on every feature map layer, or every output layer, is going to be 4. So even if we have, say, 64, we just print out the first 4, 64 the first 4, 128 the first 4. We could always modify this later on. Now for I in range 1 to the length of the activations. Now the activations have a length of 5, because from here we have this activations, which are the outputs, which is actually a list. So for I in range 1, because we're not interested in getting the 0th output, so for I in range 1 to 5, we're going to repeat this. So we're going to go layer by layer, or feature map intermediate output by feature map intermediate output. Now for the first layer we have this, and now for each channel, so we have the different channels when we have the outputs. So for each channel, in the range of number of channels, we've set it to work with the first 4 channels. So for each channel we are going to subplot in a plot. So basically we've created this axis, and then in this axis we're going to add up this subplot, which is getting this number of rows and this number of columns. Now since the number of channels equals 4, we'll get 2 rows and 2 columns to store these images in that subplot. So we have the subplot title, say channel, or whatever number we get from here, and then the axis will set the title to that, and then we plot this. Now take a close look at this plot. We have activations I. This I is to select the layer in which we are trying to get this activation. Like for example, here we have this activation I. When it's I is 0, we get the first, we get the 0th, we get the first, the second, the third, the fourth. So basically here we're selecting the layer with which we're working, since those layers constitute the output. Now after selecting the layers, the next step is to get the particular channel. Now these activations are of shape 1, 2 to 4, 2 to 4, or say shape 1, X, Y, Z. Since we have the shape 1, X, Y, Z, this one with this 0, we select the first dimension, and it's actually the only dimension. So we select this 0th index, and then for the next 2 we collect all the pixel data, and then for this last axis we select the channel which we are going to plot. So if we're on the 0th channel, we plot the 0th channel, and then if you're on the first channel, plot the first channel, second channel, plot the second channel, right up to the last channel, and then we finally show the plot. So let's run this. Feature map number 1, that's the first feature map. We have this from channel 0 to channel 3, that's the 4 channels. We have this, and then up to this last feature map. Now let's modify the code such that we could print out all the feature maps, so we will not be restrained to the first 5. So let's take this, run it on this, and there we go. As we could see, we're going deeper in the model, and as we go deeper, our model is learning now to detect high-level features as it pays less attention to the details which actually differentiate whether an image contains a dog or not. So from here we could see the different feature maps of our model. We could also go ahead to increase the number of channels. So we would say, for example, here we want, say, 9 channels. We have this 9, run it, and we're able to visualize many more channels. We'll see how we leave from model, we go deeper. See clearly how our model is able to detect different edges, different low-level features which characterize the image which has been passed as input. So that's how we visualize these models, or the feature maps, or the intermediate layers which are outputted in these models. Let's go ahead and apply transfer learning to achieve better results. We shall be using the MobileNet version 2. Now from here we could simply use this, and then we could import it right from the beginning. So let's do this. So we have from this, import MobileNet version 2. So with this, we've imported MobileNet version 2. We've imported also the global average pooling, which we shall be using, and then the input layers. We'll run this. We have the slight error. We'll modify this. There we go. So we'll get back to this MobileNet, which has been trained on ImageNet. Then from here, as we saw on the slides, we could freeze all these layers. That's from this layer to this one, since they're responsible for the low level feature extraction. And to freeze all those layers means to say that every time we're trying to train the whole model, which is made of this and an additional part for the classification, we shall not update these weights. And to do that with TensorFlow is quite easy. Basically what we do is we render this backbone untrainable. So we have backbone dot trainable equals false. Backbone dot trainable equals false. Note that this applies to for layers. So if we've defined this model, but if we have a layer, whatever layer could have layer X, for example, dot trainable equals false, and it does the same for that layer. So that's to say that if we want to render some layers of this backbone untrainable, we could just say, for example, backbone dot layers, and we'll select the particular layer and we'll render it untrainable. So we have this trainable equals false. There we go. Okay, this is normal because this wasn't defined. Now we could print out backbone dot layers 0, so you see exactly what it is. We are told here that it's an input layer, which is normal, because from here we could summarize this backbone, and we have this input layer. If we pass in this, like we move to 1, we have the 0 padding, which is basically the next layer we have. And so as we've said, if we want to render any of these layers individually untrainable, it suffices to select that layer and then you assign to this trainable false. So in a nutshell, what we're saying is this backbone is going to be run in inference mode, whereas all the rest or all the remaining parts of the model will be run in training mode. With training mode, we have the layers which are, or the weights which have been modified as we train, whereas in inference mode, which is kind of mode we use when we're testing our model, the weights don't need to be modified. So weights aren't modified, and in that sense we're basically just extracting features from this MobileNet version 2 backbone. So basically, since they have been trained on ImageNet, we just extract features and then we add a supplementary layer afterward to help us classify. So let's go ahead now to apply this. So we have this input, we define the shape, takes in 64, 64, 3. And then from this, we have X, which takes in the backbone. So the backbone takes in the inputs. And then we have X again, which takes in a global average pool. So we have global average pooling 2D, and it takes in the X. So we're using the functional API right here. We have X now. We could use a dense layer with, say, an output of which will output 1,000 neurons. We have X, and then finally we have this X, which we shall call outputs. We have the outputs, which is equals dense layer with 1,000, or rather 200, since our data set takes 200 categories, and we have the activation, which is softmax. So right here we have this X, which is passed as input, and then from this we could define a model. So let's call it our model, which takes a model. He has the inputs and then he has the outputs. So we have that. We could print out the model. We have this error at the level of the global average pool. We have this. Correct that. That's fine. So now we have the model, the summary, which could permit us summarize our model. So we see clearly how with this input, we go through the mobile net. We have this output. After global average pooling, we have this output, and then the dense layer, 1,000 neurons, and then finally this dense layer with 200 neurons. To avoid overfitting, we shall take off one dense layer from our model. So we take this off, and then we run our model. We have this new model now. And then it should be noted that every time we render some parts of our model untrainable, or all the model untrainable, or if the model was initially untrainable and we now render some parts trainable, we have to recompile this model. So even if this model had been compiled and then the trainable state of the model had changed from trainable to untrainable, or from untrainable to trainable, we have to recompile. Now we have this model.compile. The optimizer is an optimizer with learning rate of 0.001. The loss is a sparse categorical cross entropy loss. The metrics, here we have two metrics which we shall use. We shall use the sparse top K categorical accuracy. That's actually the top 1% accuracy and the top 5% accuracy. So here is the sparse top K categorical accuracy with K equals 5. If we want to take, say, the top 10%, we could take this. So for now we have the top 5%, since most of the time when evaluating the ImageNet or Tiny ImageNet data set, we have this two metrics which are commonly used. That said, we run this and then we move ahead to fit in the model. With this, we're ready to fit our model. We run this and then wait for a little while for it to load our data set and start training. We have an error right here. We're told we can't actually use the same metric, although there's a difference in the values we put in for K. So let's just use the sparse categorical accuracy, since it's when K equals 1. So we take this off, and then we have this. Run it again. We told that it's not defined, so we go ahead to define this accuracy. Right here in our definitions, we have the keras.metrics, so we import the sparse categorical accuracy. Run this, it works. We get back here and we run this, that's fine. Then we can feed our model. After training for 15 epochs, here's the results we get. The training loss goes from 2.42 right up to 0.87, and then the accuracy increases from 0.45, that's 45%, right to 77.2%. That's for the top 1% accuracy, while the top 5% accuracy goes from 70% right up to 93%. And then for the validation, we go from 1.85 right to 1.81, but nonetheless we had intermediary values like 1.69, which was actually the lowest validation loss we had. This tells us already that there's some overfitting at some point. And then for the accuracy, we go from 0.454, that's 54%, right up to 58.77%. And then for the top 5% accuracy, that for the validation, we go from 79% to a highest value of about 81.35%. Now if we get back to the LeNet model which we had done initially, we would see that for the validation, the accuracy didn't even cross 0.15, that's it didn't cross 15%. Now scrolling a bit up, we see that it actually crossed 15%. The highest validation accuracy we had was 18%. But now with the mobile net pre-trained on the image net, and we did some transfer learning, we obtained the highest validation accuracy at 58.7%. So the model, the new model with the mobile net, clearly is better off than this one. Nonetheless, with this one we trained for 100 epochs, so the model had time to overfit very much. So as you could see, the accuracy went up to about 99% for the training, but it's clear that this was so much overfitting because the validation loss was increasing as it got right up to a value of about 10.91. If you continue, you see here that the value went right up to 11.23. So that was a very poor performance of this model. It should also be noted that the number of parameters of this model, that's the LeNet model, is similar to that of the mobile net, as this one is about 2.9 million parameters and the mobile net is having 2.2 million parameters. Clearly, this model is in the state of art and can be ameliorated by using better models like the ResNet or the EfficientNet, although they'll come with many more parameters. But it should be noted that with MobileNet, the way it was conceived was for embedded devices, so we don't expect to work with too many parameters as they won't have use in these embedded devices, since embedded devices have limited resources. So you could feel free to play around with this, modify the backbone and use, say, EfficientNet B7 or ResNet 100 or any other model you can lay hands on so that you could get better results right here without necessarily overfitting. Because if you have a model with training will give you an accuracy of 99.9%, that's, say, for example, for the top 1%, and that the validation gives you an accuracy of about 21%, then that model is very useless, because in real life or when you deploying that model, the model wouldn't give you very good results, although the training set may have made you feel like the model is performing well. So it's important you note that the problem of overfitting is very serious, and it's not all about just making sure the training loss or the training accuracy is very high or the training loss is very low. So that should be taken note of. We can then plot and see what this looks like. So we've gotten from the history right here. We'll take this off. We've done this imports already. We plot the loss, the validation loss, the sparse categorical accuracy, the validation sparse categorical accuracy, the sparse top 5 categorical accuracy, the validation sparse top 5 categorical accuracy. We're going to plot all this and then see what it looks like. So clearly we have this. This orange is the validation loss, and then this blue is a train loss. We see how the train loss reduces while the validation loss reduces, and at some point starts increasing. So it's important for us to stop training at a certain point to ensure that our model doesn't overfit. That is, our model doesn't perform very well on the training while it isn't performing well on the validation. So that's very important to note. And then when we look at the accuracies, that's for the sparse categorical accuracy, the top 1%, which is the green, which is this one right here. And then for the red, the validation, this, we'll see how both are increasing, but at a certain point you have this one. Actually, we'll take this. At a certain point we have this, which stops increasing, and it kind of like settles and doesn't increase anymore while the training accuracy keeps increasing. And then logically, since the top 5% accuracy is generally more than that of the top 1%, or is normally greater than that of the top 1%, we have a similar scenario, but with the difference that the two values are kind of like approaching 1 or closer to 1. Here again, we have the validation top 5% accuracy, which is increasing, but at a certain point it kind of like plateaus, while the training accuracy keeps increasing. And so it's important that you can, or you should define and say whether you keep training or not. Another thing we could do is by adding a fully connected layer before this last layer. So we could do something like this. We add a fully connected layer before the last layer so that we could increase the model's performance, since we will have many more parameters. So we could do something like this, but while doing this, we could also add dropout to avoid the model from overfitting. So we could drop out with say 0.5. There we have this X, and there we go. Right here we have ReLU. So that's it. We could do this and then see how it affects our model. Or as we said previously, we could just simply use models like the ResNet or the EfficientNet, which although have or which are more expensive but will produce better results. So if you're building this classifier for say a system which doesn't mind having say a million parameters, and that there is enough computational power with respect to the number of operations, or enough computational power to support the number of operations, then we could go for more expensive models, which obviously will bring up better accuracy. As we've seen previously, the role of the very first layers of the model is for feature extraction. And generally, to do fine tuning, we can decide to take off or to render some of the layers which are towards the end of the model, that's the topmost layers, trainable. Unlike with transfer learning, where all this backbone is untrainable. Now recall that in order for us to make a particular layer of the model untrainable, we could do backbone.layers and then we select the index. Now if we do something like this, if we do backbone.layers and then we have the index 0, we'll find that we have this input layer. If we take index 1 for example, we have the 0 pattern. We have seen this already. So right here we have all these layers which are basically in order. So we have the 0, the first, the second, third, right up to the last. So it's important for us to know the total number of layers which we are dealing with right here. And to get this, we could simply go through all these layers that's passing through this backbone.layers up to where the index gets out of range. So here we have while true, or say while true, that will define I to be 0. We have try the backbone the layers I, and then we increment I. So we have I equals 1 plus equals 1. Then we have except, we break, such that if we go out of range, we're gonna break, and then we're gonna get the value for I, which we're gonna print right here. So print this I. So there we go. We see clearly that the number of layers we have here is equals 155. Once we have this number of layers, and then we could pick out, say, from this block 15 and decide to say, okay, we want that all this topmost layers that's up to this point will become trainable. And to do this, it suffices to simply know the index where this block lies or this layer lies. If we know where the layer lies, we are just simply gonna use a for loop and say for the index of this layer, that's the index of this layer, right up to 155, we are gonna have backbone the layers I the trainable to be equals true. But since we already have this all this backbone to be trainable, we've set it to be true. We can instead decide that we want to move from 0 to the index. So we're going from 0 to the index to 155. Actually, it's like this. So we're setting that from the index to this. We want to render this trainable, and then we want this untrainable right up to index -1. Actually, index -1. We want this untrainable. So from this, it means if we select all this, obviously in Python, to go right up to index -1, you have to go to index. So that's it, and then we'll convert this to false, since we've already run this where we have all the backbone, which is true. So that said, we're gonna have backbone.layers I trainable equals false. Now what's left for us to do is to find the index of this block 15 layer, such that we'll run all the layers from the 0th layer right up to the layer before that index, which is this, and send them or make them untrainable, since for now all layers are trainable. So right now, to get that index, let's insert a cell above and get that index. Here we're moving for I in range 0 to 155, since we've seen clearly here that we have 155 different layers. Let's take this from here. There we go. Take this off. So for I in range 0 to 155, or for I in range 155, simply we have if, that is if a layer happens to get an index which is the same as this name. So if we have backbone dot get layer, that's how we get the layer using its name. So if we have backbone dot get layer, which is actually this layer which we want to get, it's equals backbone dot layers I. Then in that case, we'll say the index, or we'll say the selected index is equals I, and then we leave the loop. So right here we could print out this selected index. Selected index is this. We initialize this. Selected index is equals 0. Now we run this, and we have the selected index to be 135. This will tell us that this is the 135th layer, or rather the 136th layer, since we started counting the layers from 0. So since we started from 0, this is going to be 136th layer, although here we have 135, and that's simply because we started counting from 0. So we've gotten this selected index, and now we can simply do this for I in range selected index, that's 135. So we want to go from the layer 0 to layer 134. You could always print this out too. You could say trainable, or rather backbone dot layers, and then you have 134. So you see here that you have this merge add, which comes just before the expand. Come back to this. So this gives us the conv2d layer, which we have at this expand. Yes, add, yes, conv2d. So that means we should go from 0 to 135, since obviously going from 0 to 135 with the slopes is the same as going from 0 to 134 actually. So I will vary from 0 to 134, since here we've put 135. So for I in range 135, backbone dot layers I dot trainable equals false. So we want those very first layers not to be trainable. So with this, we run it, and these layers are not trainable anymore. Now we shall notice the difference right here. When all the backbone wasn't trainable, we had 256,200 parameters. Now let's run this and see now the number of trainable parameters. We see that the number of trainable parameters has increased from 256,000 to 1,462,000, but nonetheless it doesn't get close to the number of, or the total number of parameters, as the topmost layers still have many parameters which are not trainable, or rather which are trainable, while the very first layers are not trainable. And so that's it. We can now compile our model. But before compiling, it's important to note that fine-tuning may bring about better results, better accuracy, but may lead to overfitting. So when doing fine-tuning, it's important to lower the learning rate. So we could take a value of 1 times e to the negative 4, that's 1 times 10 to the negative 4 rather, or 1 times 10 to the negative 5. Because if we start with a higher learning rate, the model may instead overfit. And it's also important to note that when doing fine-tuning, you have to ensure that the current data set on which you are training has to be large enough. Because if, say, you have trained or pre-trained the backbone on ImageNet, which is made of about 14 million images, and then you want to do fine-tuning on a data set with just 1,000 images, then that would obviously lead to overfitting. So it's important to take note that the fine-tuning process can give better results, and at the same time, if care not taken, you can very quickly overfit your model. In our case, our data set is 100,000 images, which is not bad, so we can permit ourselves to do some fine-tuning. Before training our model, we have to take note of the fact that for all the batch normalization layers found at the top where the model is trainable, we have to ensure that even when the other layers are trainable, the batch normalization layers should be left untrainable. This is to ensure that the model trains with some stability, as if we train or if we retrain the batch norm layers, the mean and variance statistics which has already been learned with the pre-trained model will be destroyed. So this simply means from this block 15, we started from this block 15 going downwards, and given that all these layers are trainable, we shall ensure that the batch norm layers are left untrainable. Now, to know whether a given layer is a batch norm or not, we shall use this is instance. We shall compare the backbone, the layers, and then pass the index, say for example 0, and also pass the batch normalization layer. So if we run this, see, this is not defined. Correct this, we have I here, so we are given that false. Now let's go right from this beginning and see. Here we had 0, 1, 2, 3. So if we replace this third index, see, now it's true. So that's how we test to know whether a given layer based on this index is batch norm or not. So that said, we shall now go through all the layers starting from this block 15 expand right up to the end, and whenever we have the batch norm, we render it untrainable. So we'll simply do this. We have for I in range, the selected index right up to the end. If the instance is a batch norm, then we make sure that the backbone, the layers of that given I becomes untrainable. Since for now all these layers are trainable, so we set this to false. It's now untrainable, just like the first layers. So the layers are the first parts of the models are all false, including only the batch num layers of the top of the model, which we are actually fine-tuning. So right here we have this and turn to false. So with this, let's get back to this. We'll run it again. Take this off, run this, set this. For now, let's not run this. Let's see the number of trainable parameters we have right here. We see that running this gives us this information. We shall just copy it besides. Yeah, let's copy it somewhere here. Or let's just copy it here. So let's put it right here. From this, the number of trainable parameters are about 1.4 million. Now let's go ahead and render the batch num layers untrainable and see how this number of trainable parameters actually drop, since the batch num layers are no more trainable. So let's get back to this. We run this, and then run this one now. Run it. We have 1.45. So we see that the number of trainable parameters have reduced and the number of non-trainable parameters have increased. And this is simply because now the batch num layers at the top have become non-trainable. So we could take this off now and then compile our model. Then when we run this again, this actually wasn't defined. So we've defined this, and that's fine. We now compile and then we train. After training over several epochs, here are the results we obtain. We see how the loss drops for the training data set from 5 to 2. The loss for the validation drops from about 4.83 to around 2.42, while the accuracy keeps increasing. We also see that the model trains better and faster without fine-tuning, so it's better to keep the mobile net weights untrainable. Let's now go ahead and test our model. First, we save the model right here. After saving, we have this image which we've selected in this class. Then we convert this image into an array, or first of all we load the image using TensorFlow's preprocessing. Then we convert this image or this loaded image into an array. Now note that this takes in the image, that's the path, and then the target size. Then from this we could use matplotlib to plot this image. So yeah, we'll run it, and there we go. Here's the image we're working with. Let's start from 0 because we have 500 images. We'll go from 0 to 500. So here's the image. Now we could go ahead and test it. So we basically have model.predict of the image. We add the batch dimension. So there we go. We have im array. We include this. Run that. So that's what we get. Now the problem with this is, let's print out the shape. What we get here is a one-hot representation in which the model is trying to give values to all 200 different classes, but then we're interested in the class with the highest value, and that said, we simply need to use the argmax. So we have tf.argmax, and then we do the argmax on this axis, the first axis. We could take that as -1 or just 1, because -1 is the last axis. So we could say -1 or 1. Now let's look at the shape. You see, that's what we have. Let's take this off now, and there we go. We have this telling us that this image right here is a class 0, and that's exactly the class this image belongs to. If you can recall, we have those 200 different classes. So basically we'll pick the image, which was this, in our 0th class. So here's the image we just tested. So basically now we've seen how to test our model. We could modify this input image. We could take let's take say 40. Test that. There we go. Correct classification. Could take 100. Test that. Here we have a wrong classification.